All right, so average rate of change versus instantaneous rate of change. So average rate of change, as we mentioned, is slope between 2 points, like a secant line, right? Slope between 2 points is the slope of a secant line. And of course, we have our old slope formula here, f of b minus f of a over b minus a. And I threw in this other, in quotes here, this slope here, that's sometimes called the difference quotient, for obvious reasons. It's a difference. You subtract the y's, subtract the x's, and then you divide them. Difference quotient. Okay? But you'll hear that term in your homework and stuff, so that's all it means. Difference quotient, slope between 2 points. All right. And of course, we've been saying calculus is about slope at 1 point. A tangent line. The slope, a line that touches a curve at just 1 point. So what we've done up until now is just let 2 points get really close together, right? Like we did on that one quiz question, right? Where we just calculate the slope between 2 really close points, 2 and 2.001, right? We just do a slope. But we want to do better than that. Okay? And so what we need here is there some formula where we can do that? Is there some formula where we can do the slope with just 1 point? Okay, that's our goal today. That's what we're going to try to do. So if you look over here on the board, this top thing, this is what we're headed to, right? Define the derivative at x equals a. That's where we're headed to. What does it mean to do the derivative at 1 point? Okay? All right. So if you look on page 81. Oh, I'm sorry, leave that up there. Here's the. So if you would look on page 81. At the bottom of the page, it talks about Professor X, who is driving in her car, and I don't know, it says something about it's an old car. She's a poor teacher, can't afford anything nice. And so the speedometer is broken, I think it says in there. So she wanted to know how fast she was going, so she tracked her distance traveled every 3 minutes. I don't know, some crazy thing. I don't care. We're going to fill it in later, then you can erase the question marks. All right. So on page 81, you're trying to make me look bad for a minute. All right. On page 81 at the bottom, then, you have these data points that this professor has collected on how far she had traveled at a certain point. What she would like to know is how fast was she going at 2? What was her speed? Okay, so what would we do? What could we do? Pick 2 points. Which 2 do you want to pick? 1.95 and, okay, I like the fact you guys said that now, which is interesting because we hadn't really been doing that except for that one on the quiz I talked to you about earlier, but we've been doing like some of the other classes said 2 and 2.05, right? Or 2 and 1.95, right? Which we could do, that'd be fine. But I would agree, anytime we see a table of values, I would pick one on each side. I think that's the best way to do it. So let's write this down. Here's the notation I would like for you to be using now. So this is just our average rate of change. That's all we're doing. This is still not derivative. This is estimating the derivative. Probably should put an approximation sign in there. We're just doing the approximate rate of change at this point, right? Now, one of the things that's happening in this chapter, probably should set the stage here a little bit as you're doing this. Chapter 1 was all about graphs, and we were doing slopes and estimating rise and run. Oh, we did do some zooming in on our calculator. This chapter, we're going to get more into the equations, so if you like algebra, you're going to like this stuff better than the graphs, probably. And we also have some tables of value like we have on this one. So, if I have a table, tell me what's the table value at 2.05? How much? 83.54 minus 76.54, and then divided by whatever that is, okay? so get on your calculators and do that for me. And see what we get. Exactly? Exactly 70. Okay, yeah, they're kind of rounded, so that doesn't surprise me. A lot of times it doesn't come out that nice. Okay? So it comes out 70. So now that's an approximation. That's nothing really new. That's what we've already been doing. That's average rate of change, slope between 2 points. Okay? When all you have is a table of values, that's the best we can do. All right? But we would like to do better. We would like to do better. So, we're going to do a couple different little things here. So let me come to this picture right here. All right, so here I have kind of this same situation. I would like to know the slope at this point right here. So I would like to know the slope of that line, right? The tangent line. So we could do the slope between these 2 points. Now, what do you notice? Now, here, this brings up what I was saying a minute ago. This is how we've normally been doing it. If I want to do the slope at 1, we haven't been picking a point on each side, right? We've been picking 1 and then another point to the right of it, and then letting those 2 points get close together, right? Okay? So look at the slope here. It's 3 something. It's too steep, right? I mean, look at the tangent line down here. The tangent line would be that. So if I pick 2 points here, it's too steep. If I pick my 2 points back here, it's not steep enough, right? All right, so as I get down here, the slope's getting closer and closer to what value? Looks like it's getting closer and closer to 2. We have a pretty good feeling that the slope maybe is 2 at that point. But how would we know for sure? That's what we're going to come up with today. How would we know for sure that the slope is 2? Up to this point, we've just been estimating, getting really close. And then just saying, yeah, I think it's probably about 2. All right? How would we know for sure what that slope is? Well, we're going to do it. So we would want to do a slope calculation. So for this particular one, we would do something like, so what we were doing in last chapter is we would do something like this. We'd say, okay, we're going to do f of 1.0001 minus f of 1 over 1.0001 minus 1, right? Something like that. Okay? And we would let this part of it get smaller and smaller and smaller, right? 0.000, we would add more zeros, right? So in general, what we were kind of doing was this. Excuse me. In general, we were kind of doing this. Let me just make up something here. The top was kind of that. Would you agree with that, what we've kind of been doing before? We've been kind of saying, let's pick 2 points really close together, and how close would be like h? Let's just call it. Let's give it a name, because we've been just picking numbers like 0.01 or 0.01 or whatever. Let's just do that. Now, what would be on the bottom? 2 plus h minus, but wouldn't those always just cancel? So it really would just be h, right? Because that's the run, right? It's rise over run. So how close they are, that would be the run. Okay, so notation-wise, so that's what our goal is here today, is to get into some better notation and to get a little more precise with what we're doing. Okay, so we're going to test that with a problem right here. We're going to test that with this problem right here. We're going to let f of x equal sine x. Okay? And I want to find the slope of that at 2. So that would be kind of like doing this calculation right here. So it'd be kind of like doing sine of 2.0001 minus sine of 2 all over 0.0001, right? And that would give me the sine at 2. But I'd like to do more than that. I'd like to do the sine at 2, and then at 3, and then at 4, or at a whole bunch of different points. Because if I would do the slope at a whole bunch of different points, I could graph them. Remember in the last chapter we had f graphs and f prime graphs? So if I would plot a whole bunch of slopes, I would have the f prime graph. I'm kind of curious what that would look like with sine. So we're going to do that. So we're getting used to our notation, and we're going to discover something about sine right here. So you don't have to write anything down for this. Just be ready to be oohed and awed. I can't even believe Mr. Madsen could leave. I figured he was on the edge of the seat. All right. So look. So right here, we've got Let's see, I'm going to have to get over here. All right, here's what I've done. On your calculators, you actually can, and I don't set it up right now, but you can actually do spreadsheets and stuff like that on your calculators, which is kind of cool. So what I've done here with this, what I've done with my X column here, okay, watch this. So I got 0, and then look right down here. I've got pi eighths. That decimal is pi eighths. Okay, I'm going to keep going. And this would be 2 pi eighths, which is pi fours. 3 pi eighths. 4 pi eighths would be pi halves. 5 pi eighths, 6 pi eighths, 7 pi eighths, 8 pi eighths is pi, right? All the way around to 2 pi. Okay, there's 2 pi. So I've got all those values going around the unit circle. And then over here I did the sign of those. So I did the sign of A1. Okay? So there's the sign of pi eighths. There's the sign of pi fours, which is 2 over 2, and so forth. Here's a sign of pi halves, which of course we know is 1. Now, I can take from a spreadsheet, I can insert a graph, no, a data and statistics page. Those of you in AP Stats maybe have done this already. And I can come down here and I can click and tell it what variable I want to put there. Well, down here I want the X. I think the coolest part is just how the dots move. And then on the Y I want Y1. Now watch what's going to happen. That is so cool. It gets better. Wait. It's going to get better. That's the sine curve. Right? There we go. That should be. Those are those sine values. All right. But what I want is to graph the slopes of those values. Well, let's do what we just calculated a minute ago. Let's go back to here, and right in this column, I want to calculate the slope at 0. Do you remember what we just wrote on that screen a minute ago? No? Right here. Well, it was on that other screen, but I don't want to put a 2 here because I want to be at a bunch of different points. And I don't want to put point, well, yeah, I am going to put 0.001. I'm just going to let that be really close. So I need to do this. This would be the slope of sine at 2. Well, I want to do the sine at 0 here. So I'm going to go equals to give me a formula, okay? And now tell me what to type. I'm not doing it. Yeah, don't just wait for a couple different. I'm not doing the sine at 2. I want to do the sine at 0. But in the next column, I want to do the sine of this value plus 0.001. So I want to do sine of, no, it's this one right here. But what in a spreadsheet, what cell is this? No, it's A1. There we go. A1. I'm typing this right here. I'm typing this right here. There we go. A1 plus 0.0001 minus sine of A1 divided by right there. Now, it says 0.99999, but what do you suppose it is? I'll bet it's 1. Now, think about that. The sine curve at 0, that makes sense, it slopes 1. I would say that's reasonable. Now, the beautiful thing about a spreadsheet is we can just fill down. So under menu, statistics, no, data, fill, I can just take that formula and I can fill it. Oops, whoops, whoops, there we go. I can fill it all the way down. And so what we get, now, think about the sine graph. Think about the sine graph. What are the slopes? 1, but they're getting less positive and getting less positive until 0, then they're negative and getting more negative, right? And if I scroll through these values, positive getting less positive, that'd be 0 right there. Then negative and getting more negative until right there. then negative and getting less negative till they're 0, so forth. Okay, but here, you ready? Are you sure? Get ready. Hang on. I'm going to change this. I don't want to graph y1. I want to graph the slopes. So we're about to do the derivative of the sine graph. What is it? It's the cosine. That's a big deal. Don't laugh at that. What are you doing? Look, what we have just shown right here. Think of that. We have just learned your second derivative formula. Remember we said e to the x was its own derivative? Remember that? We said that the y values on e to the x were also its slopes, which is an amazing thing. This is even, well, it's as cool. This says that the slopes, the y values of cosine are actually the slopes of the sine graph. Exactly. Exactly. The y values of cosine are the slopes of the sine. It's amazing how this stuff all fits together. So, you've just learned your second derivative formula. Okay? Derivative rule. Now we're going to learn something today where we're going to be able to come up with more of these kind of shortcuts where we know what, if you have a certain equation, you know what its derivative equation would be. All right, so we've learned also as we've been going through this, it's kind of cool, but we've also been learning a little bit about this notation that we want to be using today. So we move on to the next thing, and here's what we're going to actually come up with now today. The definition of the derivative at x equals a. And this is probably one of the two most important formulas we will have all year long. And this one is not all that useful as far as working out problems. It will be for us this week up to our next quiz, which is probably about Tuesday of next week. We will be using this formula we're about to derive. And then we're going to use it to come up with some shortcuts. And so after that, then this formula is more about the concept that it represents and what it stands for, more so than its usefulness in actually working out problems. Okay? But for this week, it'll be actually something we're using, as well as just appreciating and understanding the concept of what it means. So here's my picture. And what I've tried to do is recreate that picture I had from the calculator earlier, which was, I'll get back to it, which is this picture right here. I'm just trying to recreate this idea of 2 points becoming 1. Okay? And so that's the picture I've got here. Now the difference is I want to do this in general terms. I don't want to do it just for the slope at 1 or the slope at 2. I want it to represent the slope at any point A on any function. So I've got just some generic function f here. I've labeled a point A, and we're looking for, I probably should put that in blue. What we really want is this slope right here. We really want the slope at A. That's what we're looking for, right? We're really looking for the slope at A. But the black line is the best we can do to start. Slope between 2 points. So I've labeled the second point A plus h. That's what we talked about a minute ago. Let's let h be this distance between our 2 points. And of course, we want that to do what? We want h to become small. We want h to basically go to 0. Now the problem is, once h is 0, then we don't have 2 points anymore. We only have 1. See, and then that becomes a problem, which we're going to deal with here. And then I've also labeled my y values. If this is a, then this is f of a. And if this point is a plus h, then this point is f of a plus h. Now the reason for doing that is I don't want to do f of a and f of b here, because then I have 2 points, and I want the 2 to become 1. So what I can do is introduce this variable h, and then that h becomes 0. Okay, and so that tells us we're approaching this point A, but you'll see what I mean here in a second. So let's go ahead and write out our definition. So here it is. F prime of A, the definition of derivative, at a point x equals a. Now I'm going to leave myself a gap here because I'm going to put something in there in a minute. But this part is simply going to be the slope, right? Because that's what derivative is slope. So let's put it. Well, using this notation from the picture over here, what would I have? F of a plus h minus f of a over h, right? That looks a little different than what we had before, the f of b minus f of a over b minus a, but it's the same thing. It's still rise over run. It's still subtract the y's, subtract the x's, okay? Still the same thing. Now so this is still slope between 2 points. Here's how we make it 1 point, is what we put in front. L-I-M, standing for limit. And under that we put h with an arrow going to 0. We read that as the limit as h approaches 0. Have you ever seen that before? Okay, Mrs. Payne used to talk about it in her class, but I think maybe she doesn't get to that anymore, which is fine. The limit as h approaches 0. That's the key. That's how the 2 points become 1, is h gets closer and closer and closer to 0. Now, technically, can we let h be 0? Well, not in this form we can't, because if h is 0, what happens? Undefined, right? Yeah, you can't do a slope formula between 2 points when they're both the same point, because you get 0 divided by 0. Okay, now, we can go back to the first slide here. We can actually fill this in. So, Ryan, you'll be happy now. We can get rid of those question marks now. And we actually have our formula. Limit as h approaches 0, f of a plus h minus f of a all over h. And you look at it, it's very similar to what you see over here. Average rate of change is slope between 2 points. We go ahead and use a and b, but we could just do this part. As a matter of fact, I'll put a little color to this. The blue part here, this is simply slope between 2 points, but the red part is what makes the 2 points become 1. That's how this becomes slope at 1 point. So it's not like a brand new formula, it's just an extension of our old formula of slope between 2 points. Okay? All right. Now, how is this going to look? How are we going to use this? Well, let's go to here. All right. So, we're going to do a couple examples using this thing. One we'll do together, and then I'm going to have you try to mimic it with another problem. So, what we have here, and this is on like page 84 or something, and they say that, okay, let's take this professor who was driving in her car. And we did it, we already figured out the derivative at 2 was 70, or approximately 70. And we did this, we just picked 2 points off of that table, and we did a slope calculation. But now they're going to tell us, okay, now we know that her distance is actually this equation right here. Or her distance can be modeled with this equation right here. Okay, so like I said, chapter 2, we're going to be getting more precise, and we're going to get more into the equation part of it as opposed to the graph part of it we learned in chapter 1. All right, so we're trying to find d prime of 2. So here we go. We're going to use our formula. So d prime of 2 is, now we're going to have to flip back and forth here. Okay. All right, here we had f prime of a, but we're doing d prime of 2. So my little f's are going to be d's, and my a's are going to be 2's. Right? Everybody with me? So d prime of 2 is going to be the limit as h approaches 0, d of 2 plus h minus d of 2 all over h. Does that make sense? I I think I followed that formula pretty good. You can see it easier on your paper. Okay, it's just my function was d instead of f, and now we're going to find the slope at 2 instead of just at any point a. Okay, all right, now we've got to do a couple of different things. First of all, we got to know how we work this out. How do we do that black part, and how do we do this? Well, the blue part's easy. What's d of 2? How'd you get that? Oh, it was on that table? Yeah, but let's pretend we didn't have that table. You just plug a 2 in for t, right? D of 2. Now, that's why I had this page here. We should take a little side trip, but don't write this down. But if I tell you that f of x is this, then how do you find f of 3? So it would be this, right? What's f of a? Put a in. What's f of German shorthair? Right? Oh. I noticed you guys were looking at it. I forgot to take it. Okay, and then, so that's f of German shorthair, and then what's f of 2 plus h? 2 plus h cubed minus 2 plus h. Yeah, that's what I mean. Okay, so let's do that in black here. So d of 2 plus h would be 10 times 2 plus h. Okay, so let's get that part written down. So go ahead and do this, because you're going to have to do this. You're going to have to do it again here in a minute. You're going to have to do it on your homework a couple times. And for sure, there'll be one like this on the quiz, if not a couple of these on the quiz. By the time we get to the quiz, we'll be calling this the long one, right? We're going to come up with some shortcuts. Once we do enough of these, we start seeing some patterns and some various things. All right, now let's do the blue part. So we have minus, and then the blue would be, what did we say it was, 80? Yeah, that part's always pretty easy. And then the h on the bottom. Now, I already forgot, I hate to do that. Limit as h approaches 0. I don't want to leave that off. Okay, so let me go to my next line and give myself some room here. So limit as h approaches 0, because that's the key. I mean, without limit as h approaches 0, this isn't slope at a point, so we can't leave that off. Now we got some algebra to do. So the first part's pretty easy. That'd be 20 plus 10h plus, now we got a problem. What do you get when you square this? Very good. Do not distribute that squared. That is not 4 plus h squared. You have to FOIL that. So this would be 4. I hate to write it. That's kind of an extra step. There, 4 plus 4h plus h squared. Then we have to take it times 15. So that would be 60 plus 60h plus 15h squared, and then minus the 80. The danger here is trying to do too much in your head and losing track of stuff. So just be careful of that. Also, the minus sign is sometimes a problem. Now, not usually, because the d of 2, that's always just a number on that end, and so that's usually pretty easy, at least for the ones we're doing now. Now, tomorrow, the minus sign becomes a problem. You'll see when we get there. Okay, so that's what we have so far. Let's keep going. So what happens? 20 and 60 makes 80, which cancels that. That's nice. And actually, that happens a lot. And so what's it leave us with? 70h, h squared all over h. Now what? Factor out an h. Now, I can't emphasize enough how important this is. The whole key to this working is the fact that the 80 canceled out, and now that allows us to take out an h. And that means what? So now the h is canceled, and we get limit as h approaches 0 of 70 plus 15h. Then what? Say that again. No, not quite. And this is why it gets confusing at this point, because what happens here is we got so caught up in all the algebra we were doing. You ever hear the saying, you can't see the forest for the trees? Ever hear that saying? To not be, okay, well, I guess it's an old saying. When someone says, I couldn't see the forest for the trees, it means you're in the middle of the forest and all you could see is just these few trees around you, surrounding you. You can't see the big picture. That's what that means. Okay? You can't see the big picture because you get so caught up in the detail. And that's what happens when you get into all this algebra. So it's a good time right now to step back and say, why are we even doing this? What's that? No, that's what I mean. So, but my question to the group was, what's the next step? Right? What's the next step? What's the answer? And I got a lot of blank looks. Okay? So what I'm saying to you is, before we go to whatever the next step is, let's stop and think what it is we were trying to do. We were trying to find the slope of this function at 2. Now we use this new formula, but let's remind ourselves what this formula represents. What is this part? Slope between 2 points. And then this says let the 2 points get really close together. But then from here it was just a bunch of algebra and plugging. So we plugged stuff in, worked a bunch of algebra, we got to here. But now let me remind you, we said we want h to be 0 because that would make the 2 points become 1. But we couldn't let h be 0 because it would be undefined. But when this happened, it took care of that problem. Now h can be 0. You see what I mean? So when we were able to get the h's to cancel, this is a really critical step. Because now, what we're saying is that the slope at 2 is 70 plus 15 times however far apart they are. Well, we want them to be how far apart? 0. So we can literally plug now a 0 in for h, and the answer is 70, which is kind of what we thought it was close to anyway when we did that earlier calculation. So the final answer is 70. We literally, at the end, take and plug a 0 in for h. But don't forget, h being 0 is what makes the 2 points become 1, which is what we're trying to get, is the slope at 1 point. What this tells us is, remember before when we had the sign and it came out, the slope came out 0.99999, and I said to you, what do we think it really is? 1. Well, same thing on this problem. Now, it came out, when we did it with the table values, it came out exactly 70, but if it had come out 70.1, I just said, well, what do you think it really is? 70. But we were just guessing. We were just kind of thinking, well, if it comes out nice, that's probably what it is. Now we know. This tells us for sure that the slope is 70 plus 15 times however close they are. And we want them to not be close, to be completely close, the same point. We want h to be 0. So we know for a fact that the slope is 70, so we now have a way of doing the slope at exactly 1 point. Okay, you guys do this one. Mimic what we just did. Use the proper notation and everything. Here's a function, and here is, you want to do the slope at 2. Go ahead and do it.
Don't forget to write down that limit as you go along.
Okay, I'm going to uncover just the first line. Don't look if you don't want to, but just to let you see if you're on the right track. I really think it's important to write out the F, I call it the F notation, where you write out the formula, because when the functions get more complex, this doesn't get more complex. This part will get more complex over here, but if you write out the F of 2 plus H minus F of 2, that kind of thing, right? And then you can take one piece at a time. You can take the blue piece, and you can say, okay, what's F of 2 plus H? Oh, that means plug a 2 plus H in for the x's. What's F of 2? Plug a 2 in for the x's, right? And so you can do each of those two pieces without getting overwhelmed with the detail. You just take one piece at a time. What'd you get for the final answer? You're getting 5. Okay? So what that means is we had a parabola, and we were wanting to know the slope at 2. And I think that's probably reasonable. This parabola would be getting steep by that point, having a slope of 5. So here's what I got. If I FOIL that out, 4 squared plus 4h plus h squared plus 2 plus h. Here's where a minus might come in, kind of important. If you got a minus here, you'd have a minus. You'd have to distribute, so you have to be careful with your algebra here. But the 4 and the 2 make 6, which again cancels out that 6. So it's not a coincidence. That's going to happen most of the time. Well, all the time in these problems. Nice things will happen. So you get 4h plus h is 5h plus h squared. Then you can factor out an h, and that is the really key step right there. Because once we cancel out those h's, the thing that was the problem up here, where we can't let the 2 points become 1 because you can't do a slope formula with just 1 point. Otherwise, you're dividing by 0. But once you get to there, we can now cancel out those h's, and now that problem's eliminated. So we can let h be 0. And so 5 plus 0 is 0. Or excuse me, is 5. 5 plus 0 is 5. So there's our slope right there. So what we've done is found a way to do the slope at 1 point by taking what we know about slopes at 2 points and doing this new thing called the limit. Without limit, you can't do calculus, right? The whole idea, this is one of the, probably the number one thing about calculus is, and we're going to do this with area too. We're going to take a process we already know how to do something, and to get this new thing we need, we're going to get better and better estimates using this idea of a limit. What do they approach? What are they getting closer and closer to? That's the idea, and we're going to do more with that. Yes?
So do we have to write that
Well, when I check your work for a problem like this on the quiz, no. And if you can skip some of the algebra steps and writing out of some of that, yeah, that's fine. I caution against that because of the possibilities of screwing something up, but probably not going to get that precise in this problem right here. Now, if I ask you to write the definition of the limit, and you didn't have this, or the definition of derivative, and you didn't have that, yeah, that'd be bad. That'd be bad. But as far as when you work and I write it down every time, I even forget sometimes. But the problem is that's that whole thing about getting caught up in the weeds. You kind of forget what it is you were doing. You get down to here and you got, oh, wait a minute. What was I doing this for? So anyway. All right. That's pretty much it. The homework is going to be the 2.1 homework questions. Now, let me just talk briefly about what you're going to encounter as you get to those homework questions. There are going to be some problems where they're going to say, use the definition of the derivative, or sometimes they say, use the limit definition of the derivative, same thing. Or one of the problems that says, mimic example 3. Well, that's what we just did right there, was example 3. Okay, so they're telling you to whatever. So there'll be multiple questions asking you about this process, and in some of them you're just going to have to go through this process and work it out. But there's also going to be some, look up here real quick, everybody. There's also going to be some where you just are going to do this. There also are some problems where they just give you a table of values and tell you to estimate. Well, then they want you to just pick 2 points and do a slope. There's going to be some problems that just ask for the average rate of change. So if they ask for the average rate of change, you just do the slope between 2 points. Okay, that's what average rate of change is. Derivative is instantaneous rate of change. Okay, so those are some of the things you'll be doing in this homework. All right, I'll let you have the rest of the time then to work on it.